Who's done conjugate acids and bases before? Who hates them?
I've done, but yes.
All right, so this is another thing, you have to slow down and think about it. So a conjugate acid-base pair is going to be any two substances that are related according to the transfer of a proton. So, a conjugate acid is any base that has had a proton added. So here we're talking about transfer of protons, so we're talking about Bronsted-Lowry acids and bases, primarily. So after the reaction, the base that has the proton that's added. The conjugate base would be the acid that has had the proton removed.
Is this like redox reactions?
Sort of. I don't think it's near as hard as redox reactions, but you saw the square arrows, didn't you?
Yeah. And I saw that if it's a base, it's actually acid, and if it's an acid, it's actually base.
All right, so the easy way to do these, here's the example here. If we take ammonia and mix it with water, we know that ammonia is going to be the base, so it's going to accept the proton. So the base always becomes the conjugate acid. There is not an exception here. The base start on the left and the right here. The acid and the base are always going to be on the left side of the equation. The conjugates are defined as what they become after the mixture, after the reaction. So the base accepts a proton. So if it has accepted a proton, do we agree that in theory it can now donate that proton? Maybe it's a stretch. I get it, so it's a stretch. If it's accepted a proton, it can donate that proton back. That's what makes it the conjugate acid. The acid is the one that has the proton that's removed. And so it becomes the conjugate base. So it has lost a proton. So the acid has now lost a proton. So do we agree that it can accept the proton back? That's why it's the conjugate base.
So will it actually do it, or is it just conceptual that?
No, it happens.
Okay.
No, it happens. We're gonna do reactions with this, and we're gonna do some equilibrium reactions with this, but not yet. Not yet. So the trick here is, what about water? Water is amphoteric. Water may be an acid, it might be a base. So you have to be careful. Generally look at the other substance first. So the way that my brain works these problems might be different than how your brain sees this concept developing. That's okay. Pick the way that works for you, please. So here we're talking about Bronsted-Lowry definitions. So proton donors, proton acceptors. All right, so who can name this compound? It is H2SO4. Sulfuric acid, so guess what? It's an acid. It's an acid. But what you can also do is you can say this becomes this. So did it gain or lose a proton? It lost a proton. Yes. So yes, it has now donated a proton. So this is the acid, which makes it the conjugate base. So we're talking about acid-base reactions here. So if this is the acid, this has to be the base, but let's confirm that. Did it donate or accept a proton? It accepted a proton. Proton acceptors are bases. After they accept the proton, they become conjugate acids. So this conjugate acid can donate the proton back to this, to the conjugate base, and we can be back where we started. Does that sort of make sense? Who's working ahead of me? Good. All right. Yes, I have to draw arrows. If you don't like square arrows, you'll have fun with redox. It's okay. All right. HCO3 minus 1, also known as the bicarbonate ion. Is it the acid or the base? It's the base. It's the base because it has this nice minus sign that says, I would like to accept a proton. And you look over here, it does accept the proton. So that's the base. Bases always become conjugate acids. So if this is the base, what is water? Water, it has to be the acid. If you haven't done this before, it seems very strange to think of water as an acid or a base. It might help you to say water is acting as the acid or the base. All right, so water acting as the acid then becomes the conjugate base because it can now accept a proton. All right. I'm trying to think of what the name of this compound might be. Some sort of pentamine, probably. All right. Is this organic compound that has nitrogen in it an acid or a base? It's a base. It is a base. You can't see the lone pair, but it's there. But you can see that it accepts the proton. So then it becomes the conjugate acid. So if this is a base, water by definition must be acting as the acid, which is confirmed when you get over to the right side of the equation. And it becomes the conjugate base.
On the second one,
Mm-hmm.
water becomes hydroxide.
Yes. And hydroxide is always a base, even according to Arrhenius definitions. All right. You don't have to draw the arrows if you don't want to. If you can look at it, great. If you need a little more visual prompting, if you're a visual learner and need to write things down. All right. What's this first compound? Is it the acid or the base? It is the acid. If you're not sure, look over here. That's the conjugate base because it can accept the proton. This is definitely donating the proton. So this is the acid. Water must be the base. And that's the conjugate acid. Questions? Conjugate acids and bases. Other than that they're weird.
So what made HNO3 the acid again?
Okay.
The losing and the gaining, but
Yeah. So this is the proton here. Sometimes you have to look at it, and that's why I have to look and see what changed. So if you look at it here, and then you look at it here, it is now missing a proton. It's missing a hydrogen. Do you see the hydrogen's gone?
okay.
Okay?
I think my problem was like I didn't see. What I did was I made my arrows H3 natural kind of stuff.
Oh, okay. Yeah. Oh, yeah. You drew your arrows. Yeah.
Yeah, I got my arrows wrong. Alright, that makes more sense. Thank you.
That's good. Anybody else?